let f of x equal 4x times ln of x to the third, and consider the closed interval e to e squared. So we're asked to show that f of x satisfies the conditions of the mean value theorem, and find values in the open interval e to e squared for which f of x satisfies the mean value theorem. Okay, I got a calc problem here, and let's first of all go over what the mean value theorem states. So the mean value theorem says the following: let f of x be continuous on the closed interval ab, and f of x be differentiable on the open interval ab. Then f of b minus f of a all over b minus a equals f prime of c for some value c in the interval ab. All right, so I think seeing this geometrically helps out in terms of looking at the theorem and remembering what it says, especially when you're looking at this part right here. The part where you have f of b minus f of a over b minus a, I don't know if you recognize that from early in the class or the course, but this stands for the slope of a secant line. So let's say your function is the one there that's kind of like a sort of a gold colored orange, and you have the points a and b, and you go ahead and draw a line through those 2 points. Then the slope of that line would be f of b minus f of a. That would be your rise, all over b minus a, which is your run. Okay, that slope would equal the slope of the tangent line for some point c and a, b. That's what this theorem says. And right, it's like, yeah, you take any 2 points, your function satisfies the conditions of the mean value theorem. Take those 2 points, draw a line through them. There is some point in there where that tangent line is going to be parallel to that secant line. That's what the theorem says in so many words, geometry. Okay. All right, so the first thing we got to do here is check the conditions. Okay, that's part A. Before you calculate anything, you got to check these conditions. So first of all, is f of x continuous on this closed interval e to the third? Well, f of x would be continuous on 0 to infinity. The domain of this function is 0, not including 0 to infinity. So, and it is certainly continuous there, okay? Yeah, all the conditions of continuity would work out here at any point, and therefore it would be continuous on even that other, that interval e to the closed interval e to the third, okay? So, yeah, and you need a second or two to check this condition usually. And as a hint, usually the problems where you typically need to get more into, be a little more careful about checking whether it's continuous, is the piecewise problems. And the piecewise piecewise functions give you issues maybe with the continuity, but more than often is the differentiability. Okay, just making a point there. All right, so let's check the second condition about the differentiability. All right, so is your function differentiable on the interval e to the third? Well, if I took the derivative of my function, let's say I was just asked to take the derivative, regardless of specific point, just find a formula, I'd use the product rule, and I get 4x times 3 over x plus ln of x to the third times 4. So we use the product rule, and what I would suggest you do is just stop the video at this moment and try to calculate this yourself, just to verify. So your derivative here, if you simplified everything out, would be 12, and I'm going to put the 4 in front. And yeah, I'm essentially asking, when we say it's differentiable on that open interval, can I plug in any number from e all the way to the e to the third, not including those endpoints? Yes, there's nothing wrong here. The only issues would be if x was negative or x was 0, because ln doesn't take those values. Okay, so we're good. So now we can actually do the quote-unquote math and find the value here. So the way the mean value theorem works out is, computation speaking, is that you're going to first of all figure out what the left hand, well, there's actually either the left or right, but I like to start with the left-hand side here. I'm going to figure out the slope of that secant line on that interval. Our interval was e to e squared. Essentially what you do is you plug in your function values, your a and your b into your function. So f of e squared would be 4 times e squared ln of e squared to the third, which is 6. Ln and e are inverses of each other, so these would cancel, and you just get a 6 left. So you get 4e squared times 6, or 24e squared. F of e would be 4 times e ln of e to the third. And similarly, these cancel, and you just get a 3 left. So you get a 4e times 3, so 12e. And this is, 24e squared. A little sloppy there. So when we compute all of this right here, you would get 24e squared minus 12e all over e squared minus e. And notice you can factor an e out of both the numerator and denominator. And you could cancel that after you factor, and this is what you'd have left. So if I were you, I'd stop and work this out. Okay, so the next thing we're going to do is we're going to take what we just got and set it equal to the derivative and solve. And our derivative, once again, was 12 plus 4 ln x to the third. And yeah, we're going to go ahead and take the derivative of that. Sorry, not the derivative. We're going to solve this equation, excuse me. So I'm going to first of all subtract 12 on both sides because I want to isolate the ln. And here's what I would do. So I subtract 12 and then get a common denominator. You know, do you have to do that? Technically, no, but I think it just makes our computation more simplified here. And if you went ahead and did the math, you would just, the arithmetic, you get 12e left all over e minus 1. So I'll let you work that out. And I'm going to divide by 4, and you would get 3e over e minus 1 equals ln x to the third. And one step here that I would do is this. By rules of logarithms, we can put any exponent down in front. So using the power rule, so I put the 3 in front, and I get e over e minus 1 equals ln of x. Then finally, I would solve by exponentiating both sides. I think that's how you say it. So yeah, you raise both sides to e, and the whole idea here is e and ln cancel each other. That's why I did that, really. Okay, so you get this value. Now, sometimes you will get multiple values, but at the end of the day, you have to make sure your values fit in your interval, okay? If you did this all correct, at least one of your values must be in the interval that you're considering. In this case, that interval e to e squared, okay? But sometimes you'll come up with something that won't work. And that's not that your work is wrong, it's just the algebra or the functions you were working with makes it go wrong here. So especially when you're squaring things or taking square roots and such. All right, so what I did was I wrote what these numbers are approximately. E is approximately, e to the first, or just e, is 2.718. E squared is 7.389, and e to over e minus 1 is 4.86. So that value that we got is between e and e squared. So the value c that we're looking for is e to the e over e minus 1. Okay, so that's how the mean value theorem works. So just don't forget, please check all the conditions in the theorem, and then you can proceed to actually finding the value. Because the conditions aren't guaranteed, there's no guarantee you'll find a value. Okay, thanks for your time.